Hello, my name is Jung, Disaster Safety Intelligence Convergence Center, Electronics and Telecommunications Research Institute. From now on, I will explain disaster management technology using ICT technologies such as digital twins, network, and IoT. Prior to the development of cities, individual and single disasters mainly occurred. However, as the city develops, various facilities are interconnected, resulting in a complex and large-scale disaster. The Great East Japan earthquake in 2013 resulted in a tsunami caused by an undersea earthquake. As a result, a nuclear power plant exploded, shutting down the surrounding infrastructure and contaminating the area with radiation, which is a representative example of a large-scale complex disaster that collapsed the local community. In Korea, as the nature of disasters has changed, the existing response-oriented disaster management system consisting of prevention, preparation, response, recovery has been changed to a prediction, prevention-oriented disaster management system with forecasting and investigation analysis added. This is called a smart disaster management system, and various ICT technologies such as big data, artificial intelligence, and IoT are being used to build the disaster management system. If you look at the downtown area vertically, underground infrastructure, transportation facilities, and underground shopping malls are built sequentially underground, and these underground facilities are spatially interconnected with ground facilities. Suppose a fire breaks out in underground infrastructure such as telecommunications. In that case, underground transportation facilities will be paralyzed, and flames and smoke spread to underground shopping malls will cause enormous human and property damage. In addition, as telecommunication services are interrupted, traffic lights and elevators on the ground stop operating, which can lead to traffic accidents and life safety accidents. To this end, Korea is developing technologies to control damage by finding and solving problems before disasters occur. From now on, I will explain the technology for safely managing the underground utility duct, which is a national infrastructure facility. An underground utility tunnel is an underground facility that accommodates two or more types of important facilities, such as electricity, communication, and water supply. In Korea, a national infrastructure is legally required to be built when a new city of more than 2 million square meters is built. It is a national security facility managed by the government. Underground utility tunnel disasters spread to large-scale complex disasters such as large-scale power outages, large-scale traffic accidents, and industrial disasters, as the accommodation facilities affect various facilities in the city. We focus on prediction and prevention by developing disaster spread prediction and prevention technology, disaster risk management technology, step-by-step decision support information reasoning technology, and early and active response technology by utilizing digital twin technology to suppress disaster occurrence through simulation and developing core technologies and integrated platforms to build a disaster management system. For the development and demonstration of digital twin-based fire and disaster support integrated platform technology that enables early prediction and proactive response to fire disasters in underground utility tunnels. We are promoting real-time underground utility tunnel 3D spatial information generation and update technology, intelligent multi-sensor and relief technology for detecting fire disasters in underground utility tunnels, integrated platform for disaster safety management based on digital twin, development of disaster spread prediction and field-oriented prevention response technology, and service demonstration. We usually provide services for managing underground utility tunnels, such as manned and unmanned patrols, abnormal situation diagnosis, and risk inference. We provide fire and disaster response services such as precursor detection, initial and active response, and guided evacuation when a disaster happens. We are developing IoT and intelligent robot systems, such as multi-complex sensors, image sensors, and rail-type robots to collect on-site information on underground utility tunnels and high-availability network technology to transmit the information safely. Digital Twin is developing a high-precision 3D spatial information technology to create and manage a virtual underground utility tunnel identical to the underground utility tunnel site. We are developing analysis technology that finds problems and infers solutions by combining field information with 3D spatial information and utilizing big data, artificial intelligence, and simulation technology. The analyzed information is transmitted to the safety management system for underground utility tunnels, providing a service for managers to manage safe underground utility tunnels. Digital twin technology is critical to creating and managing a virtual world identical to the real one. In particular, due to the nature of underground space, about 32% of design and facility information for underground facilities have errors, and about 62% of power line depth information. In order to create and manage high-precision spatial information, we use CAD information to create basic spatial information, and after constructing actual measurement information using RIDA, and then by combining the two pieces of information, high-precision three-dimensional spatial information was created with a positional error of less than 5 centimeters. This slide shows high-precision 3D information. We have prepared guidelines for standardizing color information for visualization by an object as we are progressing with domestic standardization. We have developed a rail-type robot for unmanned patrol of underground utility tunnels. The rail-type robot can move at a maximum speed of 40 kilometers per hour and also provides a function to extinguish the initial fire by installing a fire extinguisher within the next 2 years. The rail-type robot also collects on-site information on underground utility tunnels through unmanned patrols during normal times. A rail-type robot collects only information on its current location, resulting in management blind spots. To solve this problem, we developed a fixed complex sensor module that can collect information from 8 types of sensors, including oxygen and carbon dioxide. In addition, a small radar device that can detect changes in spatial information and recognize objects in a haze environment has also been developed. Small radar won the Innovation Product Award at CES in 2021. We also developed a device to integrate and deliver the collected information. The underground utility tunnel is a corridor-type space with a problem. The wired network gets disconnected when the fire happens at a specific spot. To solve this problem, we built a wired wireless network environment. We developed a 5G and PSLTE router for continuous information delivery, even if the wired wireless network is lost in a certain section, to build a highly available network environment. In order to analyze various information collected from the underground utility, it is synchronized and integrated based on time, space, and events. To analyze various information collected from the underground utility, it is synchronized and integrated based on time, space, and events. The integrated information utilizes big data and artificial intelligence technology to detect abnormal events. The risk of fire and a disaster is calculated through simulation for abnormal situation events. Standards are essential to calculate the risk of fire disasters, but research is also being conducted since the norms have yet to be established. The risk management standards are being established with the risk level divided into attention, caution, and seriousness. The information collected, analyzed, and inferred through the above process is provided to the manager. When providing information to managers, it is crucial to understand and provide a variety of information intuitively. However, if intuitive information is provided, the diversity of information is reduced. Providing a variety of information takes a long time and reduces real-time characteristics. In order to solve this problem, we provide related information by configuring 3 screens. We provide one-stop service from prediction to response to investigation and analysis for managing fire disasters in underground utility tunnels. In the collection stage, information on the utility tunnel environment is collected through integrated sensors, and, in the forecasting stage, the collected information is integrated and analyzed to predict the spread of disaster and to infer the risk. In the prevention step, disaster prevention steps are performed through foreboding detection based on inferential information. In the response phase, we provide on-site customized active response services using first responder and decision support information. Finally, in the investigation and analysis stage, all collected information is recorded and analyzed to be used as primary data for damage reduction in the event of a similar situation in the future. We explain the technology for managing underground utility tunnels using digital twin technology. From now on, we will explain the technology to deliver disaster information to the public and disseminate situation information to disaster managers. A multimedia disaster information delivery platform based on 5G, UHD, local government forecasting and warning systems, and private media has been developed and installed on-site in Korea. A multimedia-based multimedia disaster information delivery platform has consisted of a next-generation integrated forecasting and warning platform to deliver disaster information to the public, a site-customized situation propagation platform for disaster management personnel, and was developed to link with the National Disaster Management Information System. We have developed and standardized a standard protocol to interconnect mobile communication, broadcasting forecasting, and warning media, and to interconnect non-standardized local government forecasting and warning systems. The next-generation integrated forecasting and warning platform delivers disaster information promptly at once by a disaster manager with one click to mobile communication, broadcasting, local government forecasting, and warning system, and private media. Similar systems include iPause in the US and a J-Alert in Japan. The next-generation integrated forecasting and warning platform automatically receives disaster occurrences with the National Disaster Management System, Air Korea, and the Early Earthquake Warning System. The received disaster information is analyzed and created as standard forecasting, and warning content is then changed into a message supporting standard protocols. The standard protocol utilizes the Common Alarm Protocol established by the ITU as a standard, and is commonly referred to as CAP. A generated CAP message is delivered to multiple media, such as mobile communication networks, broadcasting networks, and local government forecasting and warning systems. The Forecast Alarm Multimedia Gateway analyzes the received CAP message, changes it into the forecast alert message of the corresponding medium, and forwards it to the terminal. To deliver disaster information to foreigners, we automatically generate and provide disaster information in English, Japanese, Chinese, Vietnamese, and Korean. When disaster occurrence information is received from the National Disaster Management System, the relevant information is stored in a common database and provided to the public through forecasting and warning services. The disaster management system that receives the disaster information delivers disaster occurrence information to related public officials through the Disaster Safety Communication Network, PS-LTE, and automatically organizes a disaster response team using personnel information. Officials who receive disaster occurrence information recognize their role and communicate their intention to participate in the disaster response team through the terminal app. Officials in the disaster response team confirm their role, on-site response measures, etc., and initiate disaster response work. Officials report the information collected in disaster response work to the Situation Room through the terminal app. When they receive new disaster response instructions, they move to the corresponding location and perform on-site response work. This process is interactively communicated using multimedia information between the Situation Room and field response personnel. The data collected and created in this process is sent to disaster management-related organizations through API. The Multimedia Disaster Information Delivery System based on multimedia increases the efficiency of disaster management work by integrating a forecasting and warning platform and a situation propagation platform, and is expected to contribute to strengthening national disaster safety by linking the central government, local governments, and private forecasting and warning systems to eliminate blind spots in disaster information delivery. As a closing remark, the Disaster Safety Intelligence Convergence Center of the Electronics and Telecommunications Research Institute is doing its best to build a safe Republic of Korea by protecting the lives and properties of the people from disasters and providing sustainable economic activities through cooperation with the Korean government. Thank you.